to all the participants. Thank you very much for joining us in this webinar. Really appreciate your participation and your time to join us. This is going to be a good value for you guys. The investment that you do in your time discussing this subject, I can assure you that these are the topics that are not normally discussed in many petroleum engineering courses. That I know that for sure. And but in the industry, they are used, especially in certain areas, in certain certain zones for drilling. And I was, lucky to have an opportunity to work, in this area in my previous career. So I thought that we should share our experience here through this, presentation. This basically deals with the use of air foam aerated drilling, aerated mud system, and how we can use lightweight fluid. So let's get started with the presentation. So why use lightweight fluid? This is a question that we are trying to answer here today. You see, there are basically the objective is to drill non-reservoir formations in underbalanced mode with the intention to solve loss circulation problems and drill faster through hard rock formations. So let me take the second point first. In many cases, you experience hard rock formations at surface, and there is not enough weight on bit available to get the required ROP. This surface hard rock formations can become very nasty and tough, and you may end up spending a lot of time drilling through using conventional bits and conventional drilling systems. So we need to use this lightweight fluid in order to gain higher ROP and use a different method to drill through this. And in intermediate section, surface or intermediate section, you may experience loss circulation, and the normal drilling fluid may not be good to drill through. So you need to use a different technique. And this is something that is being used everywhere in the world, especially North America, in Middle East. So something that you may consider for your application as well. So this is your typical, this cartoon just shows basically in which areas you can use air drilling or lightweight fluid drilling. Basically, you can use it in surface and intermediate sections, and but not reservoir sections. So in reservoir sections, you have to use underbalanced drilling, and the focus is to prevent reservoir damage. For UBD, the focus is to prevent reservoir damage and increase productivity of a well. But for air drilling, the focus is on preventing mud losses and to get increase the ROP. The idea of not using air in reservoir or intermediate section and surface section is to ensure that you are drilling non-hydrocarbon bearing formation. Air being air has oxygen, and oxygen is combustible. So in order to avoid any kind of possibility of downhole fires, the most important condition or the criteria is to use this type of drilling methodology only in non-reservoir sections. If you have any possibility of having any hydrocarbons in the zone, then you need to go to nitrified fluid and not air. So in hard rock, if hard rock is encountered at surface, usually not enough weight on bit is available. As a result, you don't get enough ROP, that is rate of penetration. And therefore, you end up drilling this excessively. So we have seen this in India, where basically ONGC was drilling a well, and this solution was provided to them, and it really helped them in some areas in onshore surface section drilling. So number of bits were consumed to drill the surface sections. They ended up consuming some huge amount of bits, like 40-45 bits to drill just one section. When we saw the requirement, we just gave them the solution, and it was very useful. And then because each time you have to change a bit, you need to trip out a hole. So that takes a lot of time, basically, to trip out a hole and to again go back in with a new bit. You not only spend money on the bit, but you also spend the rig time to come out a hole and then go back in with a new bit. And the deviation problem due to high weight on bit. So what you have here is if you apply excessive weight on bit, you end up accidentally deviating the well. So this is another issue. So basically, there are two main criteria here as we're discussing. One is to eliminate the loss circulation issues and increase ROP and bit performance. So these are the and if you are basically in a productive zone, you protect your reservoir, increase the production. That is in that case, if you need to use nitrogen and not air for drilling, basically. But the overall objective is to save cost of drilling. Non-productive time, basically, when we talk about non-productive time, that is NPT, drilling related non-productive time, it is including the following things, Now, what happens when you encounter loss circulation? So when you encounter loss circulation, you have to use loss circulation material. And a lot of times we do this while drilling, that when we start encountering losses, we pump loss circulation material. Now, there is a cost associated with using loss circulation material. Then if your losses are not cured, you need to set a cement plug. This is complete non-productive time. And we have seen this all the time, that when you have to set a cement plug, you need to get the cementing company. Most of the time, these are all contingency emergency services. So you end up paying a lot of amount to the cementing company to design the plug, and then they come and they set this plug, and you're waiting on cement for 12 hours plus the operational time. So you end up spending 24, 36 hours just for this operation. And this is completely non-productive time. And then again, if you're going to use new mud for replacing the lost mud, then you need a lot of water. If it is a water-based mud, normally surface and intermediate sections that we are referring to is water-based mud. So you consume a lot of water to prepare this mud, and that is also additional cost. And associated costs of transporting water and water wells and all that. These are all indirect costs that get associated with the drilling, and we end up consuming a lot of materials like this, and therefore these are some of the issues associated with loss circulation. So how air drilling can help? Now, another issue that we have seen when we have a low pressure formation and you're having excessive pressure in the well is a phenomena called differential sticking. So normally what happens is, if you have your pipe gets stuck against the wall of the well, and you need and then if that happens, you need to free the pipe using basically applying over pull. And this is another non-productive time that we are talking about here. The non-productive time associated with stuck pipe. Now, if you are not able to free the pipe, then you need to go for fishing operation. That is to try to fish the pipe out of well. And then if that is also not possible, you need to set a cement plug above your fish and then sidetrack the well. So in low pressure formations, this is where you are using excessive overbalance. This differential sticking can happen in a particular area, and the cost associated with this particular non-productive activity is significantly high. And loss circulation, I just discussed, is a very common problem. And air drilling, basically what it does is it uses a lightweight fluid so that mud column and the pressure does not exceed the formation pressure. So when we know a particular basically formation having very low pressure because of any reason, either depletion or because of any kind of fractures that the formation has, then we can accordingly plan the mud system to have pressure that is lower than your that is just basically above your port pressure, but you can even be under balance, so you can plan your with this technique, you can plan your pressure in the well that is even lower than your port pressure, and that way you can reduce the issue of loss circulation. And how does it increase so we discussed about rate of penetration a little while ago. So let us see how it increases your penetration rate. So lightweight fluids basically reduce the overburden pressure over the rock face, making the rock to break easily, and basically increase your rate of penetration. This has been seen, and you would see numerous case studies and technical papers written by various authors. They have done a lot of experiments on this, that by reducing the drilling fluid density, you can achieve higher ROP. Now, we all know that drilling fluid density is always designed to prevent any influx from the wellbore. So here we are talking about drilling through a section, drilling through areas which are basically non-hydrocarbon bearing. So here, plus we have surface equipment such as the use of rotating control device, and we will see that in our coming slides. We do have a lot of protection at surface to ensure that we do not get any influx from the formation. So improved. So if you have a higher ROP, you also have the basically an ability to remove the drill cuttings faster, and you will see that with this technique you can get as much as 10 times higher ROP, and you will see the in some case studies how much of ROP was incrementally achieved. So what are the limitations of this? So now all of this appears to be very good. I mean, this seems to be a solution for everything. So why not use it everywhere, and why not we are doing it on every well or every location? So why? Because the air drilling essentially is under balance drilling. So you really need to have a very hard formation, a formation with a lot of strength in order to ensure that it doesn't collapse. Now, formations that are unconsolidated or poorly consolidated, we cannot use this technique. So it requires some kind of initial engineering evaluation to ensure that the formations are basically having enough strength to be penetrated and balanced. The other thing that you want to ensure that there are no reactive or geopressured shale. So if there are some formations that require mud to maintain wellbore integrity, such as the one mentioned in point number 2, that is reactive shale or geopressured formations. So those are the areas where you cannot use air drilling technique or aerated mud technique or underbalanced drilling technique, because those formations will start to collapse. Again, clay stones are some formations where you cannot use. You also cannot use air drilling where you have some salt formations. So there is a limitations, and before you use this technique, you need to do some engineering evaluation. And engineering evaluation and a feasibility study will give you an idea that whether this technique would be suitable. Appears to be a good one for your area, for your type of formation. Now, whether can we do it or can we not is something basically that you need to do with either your service provider or any third-party engineering company. That would be the best thing to do before you actually go for it. So, but in a lot of cases where there are I have seen where once they have established this methodology, then they have used it on a number of wells and they have got incremental benefits. As a matter of fact, in Yemen, in Abu Dhabi, in Oman, in Saudi Arabia, on a large number of wells, this is being used, and then they have been able to drill the surface and intermediate sections in a matter of few days. So by increasing your drilling rate, you can significantly reduce the cost of drilling a well. Now, when you reduce the cost, your profitability of the well increases. If you spend too much time in drilling, which is what we typically do in other areas, then your cost of well construction increases significantly. So this is one of the things that you have to take into account. So if you are involved in planning of any drilling activity, or if you are involved in research, or if you are involved in any areas, I would say that you should seriously consider evaluating this technique for your wells, to see if it can be used. And then you should approach some of the service providers, have a serious discussion with them, provide them with some data that you have, and then let them assess and give you some kind of a feedback on whether it can be used or not used. So there are some other limitations. They're written down here. So what happens is, if you're not sure about a particular section having hydrocarbons, then you should not use it, because then it can lead to downhole fires. If you have water flow zones, they can also create problem. If you have MWD, LWD is another issue where you need mud pulse telemetry. So if you have air in your mud, or if you just have air in drilling as a drilling fluid, then measurement while drilling and logging while drilling is not feasible, because as you all know, it uses mud pulse telemetry to transmit data to surface. And if you have air or aerated mud, then conventional mud pulse telemetry is not possible. You may have to use electromagnetic MWD. So there is an option available for you, an alternative available for you. So that also needs to be examined. One of the issues with using air, and why air is sometimes not permissible, is in case of any hydrocarbons present in your well from a particular zone, then it can possibly lead to downhole fires. Air being combustible gas, if it comes in contact with hydrocarbons with a certain percentage, then it can cause downhole fires. So this is the biggest risk associated with this technique, and it needs to be assessed thoroughly before we can utilize this method. Now, the other problem here is that air is also corrosive. See, nitrogen, if you use nitrogen, nitrogen is inert gas and it is less corrosive, whereas air can cause corrosion. So air can cause corrosion in your drilling equipment, in your drill pipe, in your BHA, compared to the regular mud. So you need to use corrosion inhibitors, basically to prevent corrosion. So there are solutions available, and the method and the technique is quite established. There is solutions to all the things, all the challenges that we have associated with this method. One of the other problem that happens while using air drilling is the erosion of the formation, and so you may possibly, if the formation is not hard, you may have an overgauged hole, and then that can lead to several other problems while running casing, while cementing, while the basically waiting on cement and those type of things. So you may end up using more cement. So when we talk about lightweight fluids, there are 4 main variants in this. The 4 main variants are air drilling. This is also called as dust drilling. Then you have mist drilling. Then you have foam drilling, and then you have aerated fluid. Let's examine all this one by one. So what is air drilling? In air drilling, just big volumes of dry air is used to replace the mud system. So you just use air drilling. That's it. You just use air drill. And this may sound a little unusual for those who may not have been in operation, but I have been there, and it is just called as dust drilling. Why is it called as dust drilling? Because the formation cuttings that you're drilling, it comes out in the form of dust. You are actually, and the entire, basically you're just blowing dust out of the well. So that's why it is called as dust drilling. Now, what is this mist drilling? What happens is when small quantities of water is produced by the formation while you're drilling, then a small quantity of water is added along with foaming agent to the air to mitigate the produced water, to ensure that the produced water is lifted. So foaming agent and small water is added to the air while drilling. When you start to see that the water is, the formations have started to produce water. Now you're drilling under balance, and if you pass through any water producing zones, then you would notice that there is that water needs to be also displaced out of the well, and it is done by adding some foaming agent and water to your air. This technique is called as mist drilling. So most of the time when you go to any well site for air drilling, you would go with all the required combination of options available. Like for example, you may have to switch to mist drilling while you're drilling because you see that water is produced. So you would basically take this mist drilling as the option. The next technique that is part of this group is foam drilling. Now, foam is used as a circulating fluid, and basically low volume of gas along with surfactant. Surfactant is used in foam drilling. So foam can be extremely foam. The advantage of using foam is that it has got high viscosity and has got excellent hole cleaning capacity. So you can just add surfactant, and there is some engineering calculations that need to be done to decide how much volume of surfactant you need to add, and some lab testing is also done. But a small test to see the consistency of the foam and the quality of the foam, and when the foam is generated in the well. So foam is used as part of circulating fluid. Basically, foam can give you very low density and very high viscosity. So this is the characteristics of foam, and if foam is used, it can give you excellent hole cleaning. And the last variant is aerated fluid. Now, what is aerated fluid? It is just basically combination of liquid, that is your conventional mud, and along with gas, normally air, combination of the two. Now, air is mixed. Basically, in aerated fluid, you have the entire circulating system as you have on your regular drilling operation, with the difference that you have air being added to the mud system in order to lighten the fluid. We'll see that setup, in the coming slides. So essentially, these are the four techniques that we just discussed: air, mist, aerated liquid, and foam. Depending on your situation, depending on your conditions, one other technique or a combination of this will be used for your well. For example, air drilling may be used in a very surface section. Aerated mud will be used in intermediate section drill. But the overall goal is to achieve higher ROP and minimize loss circulation. So now here you see in this basically diagram what kind of densities you would get with a particular method, a particular fluid that you'd use. So if you have air or mist, you can get a density in pounds per gallon for as less as 2 to 4 ppg. If you have aerated mud, you can get between 4 to 6.9 ppg. And if you are using oil, that is a single phase fluid, you will get between 6.9 to 8.3. And if you are using water or gel water or saturated salt water, then you would get density between 8.3 to 10. So anywhere, if you want to go below 8.5 or 8.6 ppg drilling mud density, you need to use one of this technique that we just discussed. And there are calculations and engineering assessment that needs to be done before you decide the most suitable technique for you. So let's start discussing one by one. Let's say dry air drilling. Now, the first technique that we just discussed was dry air drilling. So usually what happens is hole is unloaded from your conventional mud after you drill your cement and shoe. So once you drill your cement, once you drill your shoe track, then you unload the hole, with the help of dry air. So the mud from the hole is replaced with your dry air. And you will see these parameters. Usually when annular velocities are very high, 3,000 feet per minute, and hole is cleaned only with annular velocity. Now, you all might be wondering, how is hole cleaned? We're talking about conventional mud, which has got viscosity, which has got density. The viscosity is used to suspend the cuttings. And when you're not, and then what happens to hole cleaning? So hole cleaning usually here, the hole cleaning is done using annular velocity and not viscosity. So the velocities are so high and the particles are so small that with this high velocity of air that is being injected into your drill pipe and into the annulus will basically clean the hole. So there is no viscous fluid in the well or having any kind of properties for suspending cuttings. As we discussed a little earlier, for dry air is highly erosive, so your formation needs to be very strong, and there is no bottoms up time, unlike conventional drilling, where, as you guys, some of you may be familiar, that there is something what is called as bottoms up time. So there is a lag time depending on your circulation rate. You will need to wait for some time before the sample from the bottom comes to surface, depending on your depth and your circulation rate. Now here, there is no lag time or bottoms up time. You just get the cuttings at a very high rate to surface. There are no ECDs, and cutting at surface are in the form of a dust. So you don't have rock cutting samples at surface. It's just dust. And your ROPs are excessively high. Your bit cooling is enhanced. You have you can experience vibration in your string. There is no filter cake or mud cake because there is no mud system used. We are just using air to drill. And there is another thing, which is the use of air hammer. So this is another type of bit that is used. There is no conventional bit used. Sometimes you use a hammer bit for drilling. We will see those bits now in this in the subsequent slides. So as you see damp samples coming to surface, meaning a little bit of water associated with the samples, you switch to mist drilling. You basically start using mist drilling in order to mitigate the situation of water being entrant in your sample, and you add some water and foaming agent, which will help you clean that water from the well. And poor hole cleaning is an indication of an incremental air volume, and the use of shock sub recommended, not to be used when air hammered. So shock subs are used basically to prevent shocks on your drill string. But if you are using air hammer, then that is what is not to be used. Some other recommendations are that basically you need to frequently inspect your pipe for corrosion and erosion. Regular TCI or milk tooth bit is adequate for this application. Use of mechanical jar is more advisable because of the vibrations, and the roller reamers are also preferred, preferably to be used. Here is a typical layout. You run in your with your string, and then you have in order to get your air, in the system, you have your primary compressors, you have your booster compressors, you have your choke where you can increase or decrease your air, basically. Then you have meter run. A meter run and Barton chart recorder essentially records your flow rate of the air that you're pumping into the well. And you have your injection valve and bypass valve. Manifold basically to bypass the air. If you do not want to pump the air, then you bypass it. Uh, Basically, this is another check valve that is provided when you're before you connect to the rig standpipe manifold. And bleed off valve when you want to bleed the pressure before you have to at the time of making connection. And then you have your rotating head here, which is right on top of your POP. You have your 8 to 10 inch bluey line. Bluey line is from where your returns come and they go to the waste pit. Yeah. And then you have an option to catch your sample here. Samples are basically test, but you still need to check the sample. This is where you come to know at the sample catcher, you come to know whether you have some water being produced or not, and then whether you have to switch to waste drilling. And this is the disposal pit where all the waste goes. It needs to be far away, at least 45 minutes from the wellhead. That is one of the regulations. So you need to keep in mind that waste pit should be not very close to your wellhead. And typically, this is how it looks when you're dust drilling or air drilling. Cuttings come in the form of this dust, and they are blown towards the waste pit. Now, here is this hammer bit that we were talking about a little while ago. This can be used in place of your regular TCI bit, milk tooth bit or TCI bit. So this has a completely different mechanism. They provide very high ROPs while drilling, and they usually use the straight holes. So at very low speed, they provide very high ROP because of percussion action. Basically, it doesn't rotate; it gives you hammering action. So here is how the mechanism basically is for the bit. It operates on air, certain air pressure and flow rate that needs to be circulated through it, and it works using hammering action. This is also called as percussion action. Now, the next method that we had discussed is the mist drilling. This is applied when wet samples are noticed that the blue line while air drilling. So you remember the point where we saw that the sample is taken. So at that point, if you notice that some of the samples are wet, then you need to switch to mist drilling. This mist drilling will require more air than the basic air drilling. It's about 20 to 30% of more air. And it can handle some water influx, but low to medium, not very high water influx. If you get a lot of water in your samples, then you have to move to another technique. So if we have small volumes of water influxes from the formation, then it is possible. Again, mist drilling is also having very high annular velocities, very high velocities in the annulars, and they can cause formation erosion. So what is required for mist drilling is another pump. A normal triplex pump is required to be part of the setup to pump water into the line along with the air. And your returns are wet. So they are not like how we saw before as dust, but they are now slightly wet because you have now water in the air. So this water will cause wet samples basically to return. And some of the recommendations are that not to circulate for a long in a single spot, basically to ensure that hole is clean, and you may have to increase the air volume and concentration of foaming agent and water depending on the requirement. So this comes with experience, judgment, and some engineering knowledge. So most of the time, the supervisors and service companies that come to do this job have a lot of experience in this, and they will adjust the parameters to ensure that you don't have any downhole complications typically. So this is how it works. And then you have you need to include corrosion inhibitor as we have discussed, because use of air air is highly corrosive for the drilling equipment, so it can cause corrosion, and you need to use corrosion inhibitors as part of your chemicals that you inject. So there is a basically foam drilling is another technique that we need to consider here. And foam has an, as I mentioned earlier, foam has an excellent combination of low density and high rheology. And those who are interested in studying this topic in more details can look up on the internet how foam is used in drilling application. And essentially, it is just a very good. It has excellent characteristics where you can get as low, densities as 0.5 to 6 ppg, as low as 0.5, but it has got excellent cutting carrying capacity. So it gives you the best hole cleaning properties, and minimizes pressure surge because of liquid and gas, tied together in emulsion. Foam returns can be dumped directly to the pit or can be recycled. Foam can be recycled as well, and low air requirements for big holes. So because of the foam and its cutting carrying capacity and cutting suspension capacity, because of the viscosity now that you have, you will require lower air than normal air drilling. So foam drilling has its significant advantages. And foam drilling can also handle big water influxes. So if you get water influx while you are drilling, foam foam has an excellent hole cleaning capacity. So these water influxes can be handled very well. So this is a typical setup for foam drilling. Now here you see an additional tank of basically tank and a pump that you need to include in your setup to add as a foam basically. And the same thing that we just discussed, but we have a chemical injection pump here, and you have a foam tank where you actually create your water and surfactant, and then you add that along with your air so that foam is created. And you inject that at your standpipe manifold or before that. So it gets into the well, and basically this is how it looks on the rig side when you have a foam being drilled. If you can see here, you have your blue line here that will basically eject all the foam into your waste pit. And this is how the foam is collected on the rig. This foam can be either recycled or it is wasted, but it is environmentally friendly. So it will, with time, this foam will disintegrate. It is just surfactant and water basically. So now let's move to the next part, which is the aerated mud drilling. Aerated mud is a slightly different technique, and basically liquid phase. In this, you have got two phases. One is the liquid phase, which is your regular mud, that is oil water based mud, and basically you have to use your conventional drilling rig setup with mud pumps and everything that you need to pump this mud. And then you also add air to the standpipe manifold. So you combine your air and your mud together, and then you pump it into the well, basically to get lower densities. So the mud returning to surface basically follows the same loop as a conventional drilling. The air line is connected to the standpipe manifold, and the different drilling procedures and tripping procedures. You need to change your drilling and tripping procedures as compared to conventional drilling, because now you have air being added to the system. So it has got different pressures, and pressures need to be released sometime before you start your tripping action. And you need to probably displace well to higher density fluid before you trip out a hole. So gasified fluid is a better choice. Hole stability is a concern, and compared to, this is gasified fluid is in comparison to your air or foam drilling. And your ECDs and annular velocities are dictated by pump volume of liquids and gases. And you can control your ECD very well in this particular method. So bit is dressed with bigger nozzles to avoid high injection pressures. So your bit design also needs to change. You can use conventional bit, but the nozzles are of higher size, basically here in this case. So as I again said, the drill bit company, the service companies who are providing the services, they are all familiar with this. All you need to do is engage the discussion with them, get some feasibility study done, and perhaps a trial on a particular well to see if this technique is indeed suitable. Here is a typical setup of how it would be. Similar thing, but now here the returns are going to shell shaker. You have your mud pumps. This is the rig mud pump system pumping mud, and your air system coming from the compressors and the boosters, and these combined together. The returns are, now you have a gas mud separator. So when the returns come out, you need to separate the gas. The gas is vented out, and the mud is returned to the shell shaker and then to the tank. So the mud goes back to the rig tank and it is recycled again, be used. Whereas the gas is vented out, and you have your gas line here as it is seen to the something what is called as burning pit. Again, this pit has to be at least 45 meters far away from the wellbore. So yeah, this is the aerated drilling equipment layout, which is quite commonly used in the Middle East. Actually, let us review one case study. Here is one of the well that I was involved with. For technical reasons, I don't want to put the details of the well, but you can see what equipment was used. So normal PDC pit was used to drill a 12-quarter-inch hole section. The drilling, there was also a motor in the VHA. The size of the motor is 9.5 by 8 inch, and as you can see, nozzles bigger than what you normally see. You had jars, you had drill collars, similar roller reamer, similar BHA as you would see normally for conventional drilling. So nothing unusual, nothing extraordinary. Just that you are now here in this case you are using air along with mud, and you will see how you can get much lower equivalent mud weight in this table. If you see how the process started, and here you have your flow GPM pumping rate for the 12-quarter-inch hole section. Here you have your air in cubic feet per minute. Now you go on increasing your air, you go on reducing your fluid rate as you start drilling. And if you had been drilling just with mud, you would have had a equivalent mud density of 8.6 ppg, 8.8 ppg. But with by adding of air, you were able to get 7 ppg equivalent mud weight. Now the injection pressure is around 2000 psi, nothing unusual, very much within the range. But you can achieve between 6 to 7 ppg of equivalent mud weight by using this technique. Now, if you are drilling through a zone which is prone to loss circulation, by reducing the drilling fluid equivalent drilling fluid density, you can mitigate this problem. You can very well handle prevent loss circulation. So instead of experiencing loss circulation and then finding remedial solutions, I have seen that in many cases where people have to set cement plug, and then you drill through the cement plug, and then after that again, because there is a limitation for cement plug, you cannot have more than 250 feet or 300 feet. Cementing company will decide based on, and then you drill through that cement plug, and then you again experience losses because the losses are there. Losses are more than that height. So this goes on. The cycle goes on. Setting up cement plug, drilling through the cement plug, and you waste several days. So instead, if you use this technique, you may not experience loss circulation. You may drill through that zone, you may run the casing, and you may cement it, and that's it. So you're done with the section, and you continue towards drilling the reservoir. You can see how the ROP is significantly higher, and in some cases you got ROP as high as 196 feet per hour. And an average ROP was 80, 90, 60. So it's quite high, dramatically high in some cases as compared to conventional drilling. And then you have your weight on bit, which is nothing unusual, slightly higher than what you would normally do, but nothing unusual. Your mud properties are listed here, again, similar to what you would have normally for any drilling water-based mud. So this table is just to give you an idea about what aerated drilling is and what you would normally do. You use your compressor, your booster to get the air, and that is injected along with your fluid in the well in order to achieve lower drilling fluid densities, equivalent mud weight, and achieve basically prevent any losses or get higher ROP. So this is precisely what the objective is. Now, what do we need to do before we start the the actual drilling operation. We need to do hydraulic modeling. So let's go back to the previous chart. So where are these rates coming from? CFM. How did we start with 450? How did we start with 1,000 at a particular depth? And how was this increased gradually? Where did these numbers come from? These numbers were decided with the help of hydraulic modeling. So what do we do in hydraulic modeling, also called as the design of operation? Hydraulic modeling is part of the operations design. So what you do, you select the drilling fluid, you select the equipment. Now, if you are going to need, let's say, 450 CFM or 800 standard cubic feet per minute of air for drilling, perhaps most of you would know that 900 GPM, 1000 GPM, how are you going to achieve that? You would achieve that using your rigs pump. You have got your triplex pumps on the rigs and they would be used to drill. So this is nothing unusual, but you also need to add air to it now. So in the operations design, you need to select the equipment in order to achieve that air requirement. How many compressors you are going to need, what type of boosters you are going to need. So in operations design, you decide this equipment and also the procedure. Procedures meaning at what air you would start injection, and then how would you gradually increase to the required injection rate, at what pressure. So these are the things that you would decide in operations design. And multi-phase hydraulic simulations. So now when you do hydraulic simulations in your conventional drilling, you have just single phase, you just have liquid as your mud. Here you have liquid and you have air. So it's a combination of two. So it's multi-phase. So therefore it is called as multi-phase because your fluid system is going to have 2 or 3 phases. And therefore it is called as multi-phase. So you need a different type of hydraulic simulation here in order to decide the parameters required to drill a particular well or to get the right ECD. So the hydraulic simulation goals is to design the required variables such as liquid flow rate, air rate, and to maintain required to maintain the desired equivalent circulating density or equivalent mud weight. Now, the goals of hydraulic simulation, hydraulic modeling are to achieve, basically to ascertain that we have the desired conditions while drilling at all times. ECD is within the range. You have your right ECD available. ECD is basically you have hole cleaning is adequate, and you are within your operating window. And you would get the right size of equipment that is required to pump the right amount of volume of air and liquids and other chemicals required. And you have the safety margin maintained. One of the criteria for hole cleaning is cuttings transportation ratio. So basically in aerated mud system, you use something what is called as a cuttings transportation ratio. If you have, and then if the ratio is about 0.7, it is adequate for you to clean your hole. And if it is 0.9, yes, that is for the deviated horizontal wells. So this criteria is used to establish whether while you are drilling with a particular combination of liquid flow rate and air, you will be able to clean your hole. Because one thing we need to ensure is the cuttings or the dust or everything that is in the hole is removed, so it doesn't pack up around your BHA and cause any kind of downhole complications like stuck pipe while you're drilling. So the hole has to be clean. And remember that ROPs that you are going to get are very high. So with that high ROPs, your hole has to be clean during this drilling operation. This is a typical example well, and you will have a well profile like this. You will have a surface and intermediate casing, and then you have another whole section to be drilled. Then you use this as your input for your simulation. This is just an example for you guys to see how you typically do it. You draw your diagram. You make sure you put all the inputs like your casing, your drill pipe, your depths and your BHA details like your drill collars, your drill pipe, your heavyweight drill pipe, all other components in the BHA. So because they will all have an impact on your pressures in the well. And these are the modeling parameters. When you do hydraulics modelings, then you need to see what would be your equivalent mud weight, what the specific gravity, what are the properties of the mud in terms of viscosity. Basically, you would set your criteria that your equivalent density should be between 6 to 7 ppg. And these are the bits that you are going to use with the nozzles that you just mentioned. and the cuttings density that would normally be there when you start drilling, injection rates, temperature, what are the expected produced fluids, are there any H2S or CO2 in the well. So these are some of the things that you need to keep in mind while you're these are the inputs for your modeling basically. And these are some of the plots that you generate at the end of the completing modelings. You start your injection rate, and you have your air at 800 SCFM and 600 GPM. Basically, like you decide this is the best combination for drilling 26-inch hole section, for example, with aerated mud. And then here you have another modeling consideration for another hole size. And here you have decided that your air requirement is 1200 standard cubic feet per minute, and you have your 600 GPM as well of water rate, and all other associated parameters. After completing the modeling, you get it over here, and you will basically use that for your planning process. So once you establish this, then you know how much of air is required and what equipment you would need at surface to achieve that. So this is typically how a surface equipment is. There is a lot of different type of equipment. This is one setup that I wanted to show you here as how it looks like on the rig. When you have some compressors, you have some boosters, nothing unusual. The service company, in this case it was Weatherford, will bring it to the rig, and they will bring, you see here, these barrels over here. They are basically those chemicals that we mentioned. You need a foaming agent, you need corrosion inhibitors, you need basically some pumps and tanks, to inject these. And this thing over here is basically the chart recorder that I mentioned. This will record the flow rate of your injection, basically air. And these are the lines that are then connected to your standpipe manifold. Nothing extraordinary, nothing unusual. It's just that something that you need to discuss and decide on what equipment you need after you complete your flow modeling, and then they will bring it along. And this over here is the tool house. Basically, this is where you usually prepare your tools that are required during the operation. So interesting type of work that it's quite challenging, at the same time exciting, that you need to get involved with if required. But yes, does require some upfront planning and engineering to achieve this. And with this, I will just conclude my presentation.